Lesson 10, Polarity. So we're going to learn a new vocab term called electronegativity. And electronegativity is an element's ability to attract electrons in a chemical bond. So that means when two elements are bonded together, how much does that one element attract those shared electrons or transferred electrons? So we'll look at some examples. So first, what we have is a new chart showing electronegativity values for selected elements. Notice it looks a lot like the periodic table, except for there's no noble gases. Where we'd expect the noble gases to be over here, there's no noble gases. We'll look at that in a moment. So the other thing that's similar to the periodic table, or the same rather, is we have all of the atomic numbers are the same for each element. So atomic numbers, of course, being the number of protons in the nucleus of each element. But then these numbers down here do not match our numbers on our regular periodic table, which on a regular table would be average atomic mass. Instead, these numbers are our electronegativity values. So let's draw an arrow to one example. So beryllium has electronegativity value of 1.57. So let's look at an example to see what that means. So let's say we have sodium. Here's sodium right here, right? And we know that sodium has, because it's in group 1, we can look at our original periodic table handout, because it is in group 1 here, it means it has one valence electron. So we're going to draw one valence electron. And it would like to lose that valence electron to become Na+, because that would mean it would have a full octet of electrons in the energy level below. And then let's take an example of fluorine here. And fluorine has 1, 2, 3, 4, 5, 6, 7 electrons. Fluorine would like to gain one more electron right here to be noble gas state or have a full octet. And so fluorine would like to become F- by gaining that one electron. So fluorine has, if you notice here, fluorine has the very highest electronegativity value of all of the elements. That means it has the biggest ability to attract electrons in a chemical bond. So it's like the biggest desire for electrons. And that has to do with some concepts that we won't get into in this class, but we know that fluorine really wants to gain an electron. So we can think of it that way. It wants one electron, so it makes sense that it has a high electronegativity value. Sodium's electronegativity value is pretty low, 0.93. Actually, it's one of the lowest on the whole table. There's some other ones down here. But of the elements that we're working with this year, it's one of the lower ones. And we know sodium wants to give away this electron. And so it would make sense that it would not want that electron. It would not attract it very, very much in a chemical bond. So, and we know from our ionic compounds that when sodium and fluorine get together, sodium's 1 electron, fluorine's 7 electrons. Sodium will give that electron to fluorine, thereby becoming positive. Fluorine will become negative. They will then be attracted to each other because of the negative and positive bond, and they will form the compound NaF, sodium fluoride, 1 sodium per 1 fluorine. And that is actually the compound that they put in toothpaste to keep your teeth strong, sodium fluoride, and in drinking water. So let's now take a look at how we're going to use this chart with these numbers. So we're going to look at an example of 3 different compounds. Cl2, it's chlorine gas. HCl is actually hydrochloric acid, which is the acid our stomach makes to digest food. And NaCl sodium chloride is actually table salt. So we're going to look at these three compounds and see how their electronegativity differences compare. So let's first take Cl2, chlorine gas. So notice here we have this first chlorine has 7 electrons, 2, 4, 6, and then 7. And then the other chlorine, likewise has 7 chlorines, so 7 electrons. They both want one more electron. And because they both want it equally bad, they're going to have to share. So they share these 2 electrons, and that makes a covalent bond. And so each chlorine, this chlorine has 8 electrons around it, and this chlorine has 8 electrons around it, and they're happy, and they share those electrons equally. So let's look at the numbers. How would we use these numbers on the chart? So going up here, we're going to find chlorine. Here's chlorine. Chlorine's electronegativity value is 3.16. So what we're going to do is we're going to find the difference, and difference is subtraction. We know that from math. Difference means subtraction. So we're going to take 3.16, electronegativity value of one chlorine, minus the electronegativity value of the other chlorine, and of course we get 0, which puts us here on this, this spectrum of electronegativity differences. So when 2 elements have the exact same electronegativity, that means they share the electrons equally. So this electron cloud we see here is evenly distributed. So these electrons all hang around equally, the 2 chlorine nuclei. And then here's another picture of the electron cloud. You see it's distributed equally. It's symmetrical. Electrons are shared equally. So now let's take a look. Let's say we have hydrogen now interacting with chlorine, hydrochloric acid. So if we look up at hydrogen, hydrogen's electronegativity value is 2.2. So let's find that difference now. So we're going to have chlorine, 3.16 minus 2.20. And for that one, we get 0.96. Let's see where that falls on our kind of electronegativity number line up here. So 0.96 would be about here, 0.96. And that lands us in the polar covalent range. So the difference 0.4 to 2.0, if you get a difference value in that range, that's what's going to be called a polar covalent bond. Huh. Interesting. What's that? We haven't heard of that yet. So this becomes a polar covalent bond. Let's draw NaCl here. What happens with polar covalent bonds, actually, let's pause on that. Let's look at something we know we're familiar with, ionic bond. Then we're going to come back and see how it's different than a polar covalent bond. So now let's take sodium and chlorine. We have sodium and chlorine. Sodium has 1 electron that it wants to give up, and it very much wants to give it up. And chlorine has 7, it would like to take 1, so that 1 electron is going to transfer completely to chlorine. And then sodium's going to have a positive charge, chlorine's going to have a negative charge, and they're going to stay attracted to each other in a large crystal. That's the ratio of 1 sodium for every 1 chlorine. So let's look at how the math works out. Sodium, let's find its electronegativity value. Sodium's electronegativity value, 0.93. Okay. And then chlorine, we know, we've been working with it. Chlorine is 3.16 minus 0.93. And that gives us 3.05. So let's see, that would place us right about here. So we could place sodium chloride here. Oh, I just found a mistake I made. This is not sodium chloride here. This is HCl, hydrochloric acid. So sodium chloride is a classic ionic bond. That means the electron is completely transferred. The electron is transferred. It's not shared like we have here, or partially shared here, but it's completely transferred. So we have an ionic bond. It's in this, anything in the range of 2.0 to 4.0 electronegativity difference will be an ionic bond. All right, let's toggle back to what's going on with this polar covalent bond. So basically, it's sort of in between. It's in between these two bonds. It has, the electrons are partially shared. So we have hydrogen here has one electron. And it would like one more. It would like to share one so it can have two electrons, which would be a full valence shell for hydrogen. And then chlorine has 7, and it would also like one. So they both want an electron. But chlorine has the bigger electronegativity value than hydrogen. Chlorine wants it more. Chlorine can pull harder on that electron. So what's going to happen is those two electrons that they're sharing are going to be shared, but they're going to spend more time near chlorine than the hydrogen nucleus. And that's why we have this asymmetrical shape of the electron cloud. The electrons are spending more time over here by chlorine because it attracts them more. And then this drawing here is kind of reversed. This would be the Cl would be here and the H would be here in this example. And the electrons are spending more time by the more electronegative element than here. So the electrons are shared unequally. They're shared, but chlorine's, in this case, hogging them. That's a polar covalent bond. And that will be any compound that has a difference between 0.4 and 2.0 in their electronegativity values. The last thing on this page I want to point out is these cool little signs. So this is the Greek letter delta. It's lowercase delta. When it has a little negative sign by it, like this one, what that means is partial negative charge. When it has a plus sign by it, as you might guess, that means partial positive charge. And it's partially negative on this side here because the electrons are spending more time over there. That element, which in our example would be chlorine, has more attraction for electrons, so they spend more time there than by the hydrogen nucleus. It's partially negative and partially positive because it's not like the ionic bond where the electron was completely transferred. Right? In this example, we'd have NaCl here. When an electron is completely transferred in an ionic bond, we just use a plain minus for negative and a plain plus for positive. Okay, I'm going to do page 2 of the notes in the next video.